All right, now in this lecture video, we're going to continue looking at random effects models, and we'll look at an example of an application of the procedures that we looked at in the previous lecture video. So this is example 2.6, analysis for a random effects model, again in the context of a completely randomized design. Here's the description. A pharmaceutical company needs to examine the potency of a liquid medication that is mixed in large vats. To do this, a random sample of 5 vats from a month's production was obtained, and 4 separate samples were selected from each vat. The potency of the jth sample from the ith vat is denoted by y sub ij, with model given by the following. So we will recognize this from the previous lecture video. Y sub ij equal to mu plus alpha sub I plus epsilon sub ij, where mu is the overall mean potency across all vats comprising the entire month's production, not just the vats selected. Alpha sub I is a random variable or a random effect due to the ith vat, and epsilon sub ij is the random error term associated with the jth vat, or the jth sample, taken from the ith vat. The data, along with summary statistics, are provided on the next slide. So let's take a look at that. So here we have the raw data that have been obtained, and then we have summary statistics associated with that raw data. And you will recognize this as the same method of data organization and summarization that we used in previous examples when analyzing data for a fixed effects model in the context of a completely randomized design. So these are the sample data here, and then we have the summary statistics. And so we will use these summary statistics to perform the ANOVA, test the appropriate hypotheses, interpret those hypotheses, and so forth. So the question here, the hypotheses being tested by the ANOVA, and again, this is we have a random effects model. So what are the hypotheses that are being tested by the ANOVA? So the question, is there vat-to-vat variability in potency? In other words, is the variance associated with the vat potencies for the random effect, is that positive? Variability due to vats, or is all the variability due to the sampling within vats? In other words, the variability associated with the error term. So let me go back to 2 slides. The question here is there any variability associated with these random effects that are associated with the vats? Or is all of the variability in the response associated with the variability from the error terms? And so that is the question. So a null hypothesis then is that, in words, it would be that there is no variation in potency due to vats. All right, no variation in potency due to vats exists among the entire population of vats. Expressed in terms of the population parameter or the model parameter associated with this would be the null hypothesis that sigma squared tau is 0. There is no vat-to-vat variability across the entire population. Against the alternative hypothesis that says that there is vat-to-vat variability in the population, in words that would be expressed that variation in potency due to vats does exist among the population of vats. And we will use a 0.05 level of significance to perform this test. Now, based on the summaries, the table of raw data and the summary statistics, we saw that there was equal replication. There are 5 vats, so there are 4 degrees of freedom associated with treatments or associated with vats. Each vat, from each vat, there were 4 samples were selected. All right, and so we have 20 observations total. So we have 19 total degrees of freedom. And then we have 19 minus 4 or 15 error degrees of freedom in the ANOVA table. All right, so taking a look again here at the raw data and these summary statistics, we're going to use these various summary statistics to come up with the quantities that we need to calculate the sum of squares total, the sum of squares for treatments, and then we'll get the sum of squares error by subtraction. Okay, so we first calculate the correction term. And again, these calculations are the exact same calculations that we did for the fixed effects model in the completely randomized design. And so this correction term is the square of the overall sum of the observations, 62.7 squared, divided by r dot, which is the total number of observations. So we divide the square of 62.7 by 20, and that gives us 196.5645 as our correction term. Then to get the total corrected sum of squares, we calculate the sum of the squared observations. Going back up here, all right, we see that that would be, what we've done here in columns is calculate the square, or the sum of the squares of each data value in each column, and then we're just adding up those sums, and so we get 209.89. And then from that we subtract off the correction term, and so we get 13.3255. So that is the total corrected sum of squares, and that will go in the ANOVA table. Then to get the treatment sum of squares, we have to square the sums from each of the samples, divide those squared sums by the sample size within each sample, add those quantities up, and then subtract off the correction factor. And so we square 13.5 divided by 4, square 10.3 divided by 4, and so forth for all 5 samples. Add those up, and we get 208.5125. We subtract off the correction term, and we get 11.948. All right, and so then we can plug those values into our ANOVA table. Once we have those two values, we know that because the treatment sum of squares and the error sum of squares have to add up to the total sum of squares, we can get the error sum of squares by subtraction. All right, and so that's very easy to do. And now we're off to the races. Once we have these two values, we can compute the corresponding mean squares by dividing a given sum of squares by its degrees of freedom. All right, so to get the mean squares for treatments, we divide the 11.948 by 4. To get the mean square error, we divide the 1.3775 by 15, and so we get 2.9870 for the mean square for treatments, and a 0.0918, the mean squares for error. And then once we have that, again, we take the ratio of those two numbers to get our F statistic, which is 32.53, so quite large. So the F statistic here is very large. Remember, we're looking for values that are bigger than 1 to lead us to reject the null hypothesis. Now here is just a spreadsheet that I've implemented, very similar to the spreadsheet that I showed you in other examples. In fact, this was just I just added a column here so I would have the columns for the 5 VATs and so forth. So that's really the only change I had to make other than entering the different raw data. All right, you see here that we have the same F statistic to 4 decimal places here, 32.5263, and the p-value for this test, we did not have it on this page, but we can see here that it calculates the p-value for us, and it's equal to 3.13 times 10 to the negative 7th. So a very, very small p-value. This F statistic is very significant. All right, it's very large. The corresponding p-value is therefore very small, and so that tells us there is strong evidence against the null hypothesis that is being tested by this random effects CRD ANOVA. And so what hypotheses are being tested? Well, again, the null hypothesis is that sigma squared sub tau is 0, and that is equivalent to saying that there is no variation, or that no variation in potency due to VATs exists among the entire population of VATs, against the alternative hypothesis that says that sigma squared sub tau is positive, indicating that that variation in potency due to vats does exist among the population of vats. All right. Now we're using a 0.05 level of significance. Again, this p-value is very, very small, right? And so we know just based on that we would reject this null hypothesis. If we are using the critical point, the test statistic and critical point method, again, we would see that we would reject. I mean, the F statistic is more than 10 times larger than the critical point, which was 3.06. And so because of that, either using the test statistic, critical point method, or using the p-value method, the results are equivalent. We reject the null hypothesis and conclude that variation exists in potency among the population of vats. All right, so let's proceed further. Now what we want to do is to estimate the variance components in the model. Remember that the variance components consist of the variance of the random error term, the epsilon. The epsilons is one for each of the observations, and then also the sigma squared sub tau, which is the variance component associated with the random treatment effect, or the random vat effect. And so estimates of the model variance components can now be computed from the mean squares in the ANOVA table. Remember that the formulas for computing these variance component estimates come from the values, the mean squares, in the ANOVA table. And so the sigma hat squared, the variance, the estimated variance of the random error terms is given by the mean squared error in the ANOVA table, which we found to be 0.0918. The estimate of the variance associated with the random vat effects, sigma tau squared, the estimate is denoted sigma hat squared sub tau, and that is given by the difference between the mean square treatment minus the mean square error divided by the common sample size within each of the vats. Okay, this is in this situation where because of the equal replication, this formula simplifies to something very nice. And anyway, so we see here that sigma hat squared sub tau is equal to 0.7238. So again, based on the hypothesis test that is being performed by the ANOVA, we've concluded that this variance component is non-zero, it's positive. We've concluded that it's greater than zero. So what we wanted to do after this is then estimate what that variance component is equal to, and this is our point estimate for that, that estimate. All right, now once we have these variance component estimates, we can do things like estimate the variability associated with the estimates of the overall mean. And so let's first look at estimating the variability of the overall mean estimators based on the individual sample means. Now again, because of the equal replication, the variance, or the estimated variance, of the sample means will be the same for all samples. And that's what we're saying here. Now, the estimated variance of a sample mean, which is again denoted by each of these pieces of notation here, is given by sigma hat squared sub tau plus sigma hat squared over r sub I, which we just computed those two on the previous slide. And so we get a value of 0.74675. Now, to get the estimated standard error of y bar sub I, we take the square root of that and we get 0.86415. So that is the estimated standard deviation of the sampling distribution of each of the sample means. And each of those sample means, remember, is an unbiased estimate, or provides an unbiased estimate of mu, the overall population mean potency across all vats in the production run for the month. Now let's do the same kind of thing, calculate the estimated variability associated with the overall mean estimator, but using the combined sample, right? Remember, when we're using the combined sample, we're talking about the overall combined sample mean, y bar. And so the estimates of the variance and standard deviation of y bar, the overall combined sample mean, are given here. And we use these formulas. And so we see that the estimated variance of y bar is equal to 0.14935. And the estimated standard error is therefore the square root of that, which is 0.38646. Okay, so putting this information together, so again, we're wanting to estimate the overall potency across all vats and the population of vats for that month's production run. All right, and so that mean is mu, and it's unknown, but we're estimating it. And I'm just including here the individual estimates from each of the 5 samples from each of the 5 vats. And then for the combined sample as well. And so we see here that the estimated potencies for the overall population potency across all vats using sample 1 would be 3.38 units. For sample 2, 2.58 units. For sample 3, 3.43 units. For sample 4, 4.28 units. And then for sample 5, 2.03 units. Now remember that each of these is providing an unbiased estimate for mu. Now, when we combine all the data, we get a combined estimate of mu equal to 3.135. This also is an unbiased estimator for mu, the overall potency across all production vats for that month. So we've got 6 estimates for mu. And a question would be, which one should we use? Well, we want to use the one that is the most reliable, all right? And how do we assess that? Well, we have to look at the variability associated with these different estimates. And again, I'm including this just for illustrative purposes. Based on what we just computed on the previous slides, the estimated standard error for the estimates provided by each of the sample means, they're all equal to 0.86415. The estimate provided by the combined sample, the estimate of the standard error of y bar from the combined sample is quite a bit smaller, 0.38646. And so you see here that obviously the estimate provided by the combined sample is much more precise an estimator of mu than is the others, because the variability associated with that point estimator is smaller than the rest. So, we would not use the individual sample means to estimate the overall population potency. We would use the combined sample. I've just included them here to show you why that is, okay? Because we want to use the estimator that has the most reliability. It's the most precise estimator for mu. So that's what I wanted to show in this lecture video, an example of how to analyze data for a random model, random effects model in the context of a completely randomized design. What we saw here is that the calculations, at least for the ANOVA, are exactly the same as they are for a fixed effects model in the context of a completely randomized design. The differences are in the hypotheses that are being tested. The hypotheses that are being tested are necessarily different for a random effects model than they are for a fixed effects model. However, the underlying interpretation is very, very similar. The one difference in interpretation is that the inference space for the space to which our inferences apply in the context of a randomized model is broader than it is for a fixed effects model. But really the underlying type of question is the same. Is there VAT to VAT variability? So with that, we'll end this lecture video, and we will continue on in the next video.